strongest one, or a strong one, was between the Apollo 16 and 17 missions. It's a well-known event. The one was the Apollo 16 was in April or March maybe. The other one was in August, and sometime in July or something, there was a huge coronal mass ejection, which caused the radiation load, which would have been comparable to the radiation loads at the time and on the roof of the Chernobyl plant got. Right. So they would have survived maybe the mission going home, but they would have been dead in the week after, next time after that. I'm even shutting down right now, but it doesn't even shut down.
Those are timescales which are days, weeks, months, not 11 years. Or
yeah, but you saw that the solar flare index was correlated to the solar cycle. So you had more of them during the peak thing. So if you want to go out into space, you have better chances in the solar minimums. But because then you had cosmic rays to worry about.
Well, they are not so dangerous.
So that the chance of getting a cosmic ray in the head might be something.
so is the idea then to get short-term forecasts good enough for one-week missions when they're likely, or just to try and only send missions when they're unlikely?
Both.
I think we would be thinking about a shorter-term prediction, maybe on the time scale of days, and of course in the last instance, maybe minutes before a very serious impact.
What's the delay between the light and the particle?
So the shortest delay that is meaningful, I think, is on the order of minutes.
So if you were on the moon, you could go inside, but if you're in space,
the
return of satellites is the main thing. Because they arrive.
Yes, it is not even clear whether you have any protection that you could possibly make use of. Because
on the moon or in space?
Both. I mean, outside the Earth's orbit in any case. And the reason is, I know something's happening.
Yeah, got it.
The reason is that if you have a big shield of lead, for example, that slows down rapid, fast particles, and that causes perhaps even more damage. So you need to not only slow them down, you need to slow them down so that you don't even penetrate further. I think that would be the issue. So it's, and that's what I meant by...
so what happens if you're on the space shuttle?
Yeah, no, then you're in the Earth protecting magnetosphere.
Okay, yeah.
Which you don't have when you're going to the moon.
But there is actually conspiracy people that claim that the reason we can't have gone to the moon is because the astronauts would have been fried. And that is an argument that people...
So
So I have a few things that I could maybe highlight, and I shouldn't make it too long perhaps. But Andreas mentioned already the basics about the sun. What we are interested in is the outer 30% by radius, because it is a layer where we have turbulence. And turbulence is able to convert kinetic energy into magnetic energy. And this is manifested in terms of sunspot measurements. We have seen here what we called an oscillator. There's also a spatial component to this, in that the sunspots appear at the beginning of the cycle at high latitudes, and then closer to the end of the cycle, or closer to the maximum actually, at lower latitudes. So spatial temporal coherence, which you also see in magnetograms. Here's a magnetogram which goes all the way to the poles, it's cosine of pole latitude, and you have a magnetic field that has systematically the opposite sign in north and south, and it switches from one cycle to the next. So this is a remarkable large-scale spatio-temporal order. The question is, why do we have that? Is it just some random oscillation, as we were thinking, or is there really something like a clock behind it? If you see that, would you think it's something like a biennial oscillation? And
so that this is more like a switch. I mean, the polarity switch is more like it's a switch between consecutive cycles. So it's not so much the timing as something about the magnetic field. And we only have data back to.
Actually, I mean, these butterfly diagram that more resembles the QBO. Actually, you have a drift. You have a mean flow sort of drifting away, very superficially. This looks pretty close to that.
Here a picture which displays the standard idea which has been developed over several decades, also many decades ago. One important ingredient is believed to be differential rotation. We know from observations that the equator is rotating faster than the pole by 30%. It's a large differential rotation. But there's also differential rotation with depth. There is, and this is slightly too small perhaps, this is 0.7 relative radii. This is the bottom of the convection zone. In the bulk of the convection zone, you typically have at low latitudes, 30 degrees latitude and 0 degrees latitude, you have a positive gradient, but near the surface you have a very large negative gradient. The angular velocity as a function of depth. This is angular velocity as a function of radius. And so if I am now looking into the surface layers in particular, for reasons that I can comment on afterwards, then we see we have a large negative gradient, so that means it's faster in the inside. So if you have a magnetic field line which is pointing into the sun now, then the tip of this vector will be moved inwards, and so you produce a positive toroidal component, one which goes eastward, as you see here. Now, this turns then a poloidal magnetic field into a toroidal magnetic field, and likewise on this end it's going in the opposite direction. If you didn't have any turbulence, that would be the end of the story. And by the way, the origin for differential rotation lies actually in the fact that you do have turbulence in the sun, and the turbulence is anisotropic. So if you didn't have any other effects, then we would see then we would just see the toroidal field. Nothing else would happen. But we do have turbulence in this system, and what can happen is you have motions that are convective, but the medium is highly stratified. So if the motion, a particle goes upwards, it expands. And so as it expands and draws with it magnetic field lines, it will be tilting because of the Coriolis force in the clockwise direction here. Systematically in the same direction, because expansion together with rotation, expansion together with the Coriolis force gives you a systematically positive toroidal component here. So if you now draw this toroidal component in a side view again, it would look like this. And look at the orientation here. It goes downward on this edge, which looks similar to the loop over here. And so you see then that you have a similarly looking loop half a cycle afterwards, which has migrated somewhat to lower latitudes now. And so this picture would explain, at least at a qualitative level, why you have an equator migration. And here you have the generation of a new loop. So this is the pictorial picture. It may not even work that way, because it may not even, the whole thing might actually decay in the end. Because what we have to rely on is that the magnetic fields that you're producing, and that is losing energy against ohmic decay. Resistive heat is being produced. The heat must be supplied. And it must be, in principle, supplied by the kinetic motions. And this may or may not work, this process. So you actually need to work this out mathematically. This has been developed for some decades through mathematical theories by looking at the induction equation. The magnetic field is governed by the Maxwell equations, and together with Ohm's law, the electric field, or the negative electric field, has a component from U cross B, and it also has a resistive component. So if you put it all together, then you get this equation, which has a dissipation term, and it has a convective term, which looks like this, U cross B. This is called the induction equation. And this equation you can average. If you average this equation, and we want to average because the overall behavior, and we are thinking of toroidal averages. And the reason why we are thinking it might make sense is because the mean magnetic field that we see has a very clear pattern even after averaging. Okay, so therefore we average this equation, and of course we get the product of averages, but we also get the product of the fluctuations averaged. Lowercase letters indicating the fluctuations, and this has been expressed in terms of the calculation in terms of the theory for the fluctuations, which lead to a term which is proportional to the mean magnetic field, and that's this term here. It's proportional to h bar. H is here the mean magnetic field. And there's some coefficient in front of this. One has to do with rotation, omega, here lowercase in this case it's written, dotted into the gradient of this radification. And that is exactly what represents the effect of Coriolis force. Coriolis, or the effect of cyclonic events. So cyclonic events you get if you have a rotation together with stratification or non-uniformity of the medium in one direction. So then you get this, and this has been calculated explicitly. So if you then put it all into a simple one-dimensional model, so remember now we have a term then from u cross b, which actually has a component parallel to the mean magnetic field times some coefficient that we in the following call alpha.
So this depends on some kind of closure.
And that is a closure, yeah.
So there is some arbitrary assumption given here, I guess.
They don't have to be arbitrary. They can be fully justified if the magnetic Reynolds number is low. If the magnetic Reynolds number is high, then they become more dubious, yes. But then you can make contact with simulations. I can show a few pictures about that. And then all of a sudden what might be dubious is actually confirmed up to the magnetic Reynolds numbers or the fluid Reynolds numbers that you can actually simulate. And so then you have to come up with arguments why that actually wouldn't make sense for higher Reynolds numbers, if that's the belief, which is indeed a non-trivial question. So you mentioned closure, yes. So the closure will produce not only a new term like alpha, it might actually and should actually also produce an enhanced viscosity or resistivity here. So I should call it, and I do call it later on actually either capital T, and this should be also either capital T. So the model, the process that these equations are describing then is one where the toroidal field is being turned into a toroidal field by the differential rotation, called the omega effect, and then likewise the toroidal field through these cyclonic events, called alpha effect, produces again toroidal magnetic field, which is this equation. Toroidal magnetic field is Bx, toroidal magnetic field is By. In principle, an alpha effect will also operate in this equation, but it's weak compared with that, with the effect of shear. So this is now a simple equation, which has a chance of being actually accurate, except that the alpha is in principle a tensor, eta is also a tensor, and there could be other modifications that would, of course, change the picture. But apart from those things, in principle, it can be an accurate theory. And so this is, at this level, if you assume alpha to be independent of the magnetic field and other things, it's a kinematic theory. And so then you can, of course, if you assume these coefficients to be even constant in space, you can just put in calculate the dispersion relation from this, and you find this following equation. You find a damping term from these here, and you find another plus minus square root of ik alpha into shear. Now the square root of the imaginary unit gives you, it's 90 degrees in the imaginary plane. The square root is 45 degrees, so that's I1 plus I, divided by the square root of 2. And so what you then have is, first of all, a term that one of the two solutions can have a positive contribution, and that can balance dissipation. So you can actually have an excited solution, or you can also have a marginally excited solution. So the question whether or not the dynamo is decaying or not is now quantitatively accessible. It just depends on whether alpha is big enough compared to eta t. It also has an oscillatory component. The solutions here are assumed to be proportional to e to the lambda t, so imaginary components correspond to a frequency here. And then the frequency depends exactly again on alpha and shear. So there's even now a theory for why you could have it, for why there might be really an oscillation. And that comes from straight mathematics by averaging the equations. Okay, so this was basically assuming just mean field theory. Now the question is anything like this borne out by simulations? And that has been a long time. So remember, the alpha effect was invented first already in 55, mathematically developed in 66. And even by the year 1981, it was still not clear whether that is a theory that actually works. So what people have been seeing for the first time then is in helical turbulence. I say helicity because helicity is what represents, of course, the cyclonic events. Cyclonic events correspond to fluid motions that are helical, with negative helicity in the north and positive helicity in the southern hemisphere of the Earth's factor. So what they see here, Meneguzzi et al., is magnetic energy that is increasing with time. And that was all that they were able to calculate on a Cray 1 computer at NCAR back in those years. Even 10 years later, with the 128 cube simulation, they saw a magnetic field that had now reached saturation, but it was by no means clear that the magnetic field had actually a large-scale component. And it was dominated by small-scale stuff. Another almost 10 years later, you saw evidence for larger-scale patches in a simulation which had large-scale separation. Scale separation meaning here that the energy is injected in an isotropic turbulence model, which is helicity, at a wave number that is high compared to the wave number of the box, which is this wave number. So you have scale separation between the driving scale and the rest of the domain. And indeed what they see is magnetic energy growing on a scale that is larger than the scale of the turbulent motions. And so that was the state of the art back then, and in the meantime, or even just a few years later, I had calculations which demonstrated this much, much more clearly. And you see here really a large-scale field covering the entire domain, which is here a periodic box. So now you can ask what the hell does a periodic box has to do with anything? But remember, we have started by writing down equations, which where an alpha effect popped up, and one of the questions is, does an alpha effect even exist? So now you can ask this question under solar conditions, but you can ask this question also under all kinds of other conditions. Because if once you have a correct mean field theory, that should be applicable and testable under various conditions. Various conditions, various boundary conditions, of course, give you different types of solutions. So in this case, if you have a periodic box, the solution that you should expect then is one where the large-scale magnetic field is nearly force-free, and such a magnetic field is a so-called Beltrami field. It has the structure, for example, cosine z, sine z, and 0. If you calculate the curl of this, then the curl of this is equal to the magnetic field itself. So it's an eigenfunction of the curl radar. In this case, with a minus sign. Indeed, that is the type of solutions that are borne out. What you have, of course, is a large-scale component, which is, of course, superimposed on the remaining small-scale motions, which are responsible for driving this large-scale field.
So this is the structure. The large-scale field should be a Bertrand field.
That
is the field selected by this alpha omega.
Exactly. Yes. On a scale that is large compared to that of the box, in this case the driving scale was at the wave number 5, and so you expect a large-scale magnetic field on a somewhat larger scale, but here it has reached the scale of the entire domain. We might come back to that.
This is without shear, right?
In this case, it's without shear. Now, if you add shear, you find also a large-scale component. Here is shown the z-coordinate. You see, if you go along the z-coordinate, you see again a sinusoidal modulation of one of the components, here the By component. But as a function of time, this magnetic field now starts to propagate, exactly as predicted by that mean field equation. So the mean field equation gives you, of course, a frequency, omega, and you get your wave number, and if you differentiate the two, then you get a phase speed. And that's the phase speed with which this wave is propagating in space. And so the sign of the propagation depends on the sign of shear, and also on the sign of the helicity. And that is all very well borne out. Now these in both cases were artificial flows, where the turbulence was driven with an imposed forcing function, which has no physical reality really, except that it allows you to make contact with analytic theories, many of which are isotropic. No flow in reality is ever isotropic. Real flows are anisotropic for the reason that there must be something which drives turbulence. One reason for driving turbulence is convection. If the convective flows become sufficiently vigorous, you produce turbulence. And here's shown in a simulation by Patrick Kepler, which as a function of time shows you that you find a magnetic field that has two different polarities in the upper parts of the convective domain, Z, and the lower part of the domain. These are the two different components, Bx and By. So this is an example of a non-oscillatory solution. Here is a completely different situation. That's one where you don't have convection, but you have a large-scale magnetic not even a large-scale magnetic field, but we believe that this is, so this is first of all in a model where there's strong differential rotation. It's a model of the accretion disk, of an accretion disk. Now, if you did have a magnetic field, together with shear of the right sign, that will become unstable. And that's called magnetorotational instability. So it requires a magnetic field to be present in order to get the turbulence. But if you have the turbulence, you can produce magnetic fields via the dynamo effect. So it's clearly a much more complicated system because it is a system that requires a doubly positive feedback between two different mechanisms. Anyway, so there we have an oscillatory solution, or an example of an oscillatory solution. Here's shown a low resolution calculation of the same thing now, is shear and helically forced turbulence again. The reason why I show this is because I want you to realize that the way that you have a magnetic field that is oscillating and propagating in space, I keep here my position fixed and you see that the magnetic field is gradually moving upwards, is something that really it takes many, many turnover times. So if you want to understand this in terms of simple field line motions, it is highly non-trivial, or it may be not possible.
What does the color mean?
The color means one component, the Y component. And so in any of the magnetic field components, you would see the migration of the magnetic field. So it's driven all the time, the magnetic field, but you see a large-scale component. Here's an animation that Gustavo prepared.
And there is a mean flow here also.
There's a mean flow, yes, and the mean flow goes in this direction, in the horizontal direction. This is the x direction, so the flow goes in the y direction, which is this one, but depends on x. So it's fast in this direction and slow backwards in the other end of the box.
I mean, this looks very much like QBO also, doesn't it?
Yeah, so maybe if that's the case, one wonders...
Descending gradually through the stratosphere.
Yes, yes.
Yeah. And so the first case would be if there is really similarity, this is really driven by some kind of wave. But on the other hand, well,
Breaking waves.
breaking waves, yes.
So would it not be possible in that case to think about such a mean field theory for the QBOs?
No, well, I think the QBO is pretty well understood.
In terms of...
In terms of waves, the waves propagating from the troposphere and upward, and carrying momentum with
Yes.
and as they break,
And
they deposit momentum in the mean flow in the stratosphere, and that accelerates the field flow, and then you can see how this feedback is that
Yes.
the acceleration means that the profile goes down, and so I think there is no point in trying to put some mean field theory or stochastic things into this. It's pretty much, of course, in some sense, it's a stochastical field or waves propagating upward, but they simply drive the system in the QBO.
But how do you explain that? I mean, when you say it's actually well understood, what do you mean by that? Can you actually tell...
Well, there is a famous experiment that looks like this. Lab experiment. I think that was sort of the first thing they have. You have a rotating box, I think. You've seen this?
Yes.
Yeah.
With the things at the bottom.
Yeah, that's right.
And that what is...
And you have a stratified fluid. Yeah, you have so it's stably stratified here. And you have a possibility for internal waves, and then you can have some, I don't know, some pistons or something moving up and down in the bottom.
Yes, right.
And then, it's resting from the beginning, and after a while you see these exciting turning waves going up. And after a while they start exciting in inflow, and you get a vertical profile that looks something like this, So here it's like this, here it's like that, it's inside this box.
Yes.
And these are gradually descending. And it's clearly understood theoretically how, that these turning waves generated down here, they deposit their momentum, and they do this at the lower edge here. So here is a good way to deposit.
The propagation characteristics depend on the sign of the whether the wind is.
But you do need
They deposit the momentum in a critical area.
Yes.
And then that critical area is below the jet itself. So therefore the deposit is for momentum here, and that will sort of shift it downwards.
But
So it's a clear, I think there is a much more detailed dynamical understanding here that you get from something in theory.
so but you do need a piston which moves up and down at what?
Yeah, in the atmosphere you have a piston.
And but the frequency of the piston is much higher than that of the oscillation, isn't it?
Much higher.
It's much higher. And so
In the atmosphere, they're called gravity waves. They're not gravity waves that you would. They're just flow over mountains or convection or something like this, firing off these fast waves.
I'm speaking here right now. Yes.
It's all the same.
Okay. Okay, no problem. Yes. Yes, I don't have time right now, but thanks. We can talk later, right? Bye.
Someone disagreeing with the QVA theory.
What?
No, sorry.
I mean, the period here, talk of this. The period QBO, these 2 years, is, the time it takes for this to descend to there. And the period, it's like you force the waves, and the force you force, the more waves you have, the faster this profile will descend. But there's no oscillator.
Yes. But the period is locked to be 2 years, or can it be actually 2.5 years?
It's 2 and a bit, so that's why it's called the quasi biennial.
It's maybe, I think, average 28 months or something.
It's not quite 2 years.
A little bit more than 2 years.
Is it related to the seasons?
Not
Is
really.
No, it's completely
It's not locked
independent.
to the
It's not locked down or something.
Yeah, right. I mean, first of all, I know that there's often criticism that you don't need to have a simpler theory if the more complicated one works, but or maybe you would call it a simpler theory. The mean field theory would be a more complicated one. But first of all, I'm not sure whether we actually are talking about something that is applicable to the sun in this case. It should be checked, of course. And
But it certainly looks similar.
yeah. Yes. Right.
I mean, you have a lot of high frequency waves here, bouncing up and down. Probably some of these are, deposit their momentum somewhere, and this has to be critical waves.
But in this case, it's not momentum they're depositing, right? It's magnetic field or something.
Yeah, but it's time to also zone the flows here.
Yeah.
And where are these generated? These waves, fluctuations are generated basically in a stochastic fashion everywhere by some numerical, you inject small-scale numerical fluctuations.
You have a forcing term on the right-hand side of the momentum equation, yeah.
And that's stochastic and everywhere.
If that's what you have, if you have convection on the other hand, then of course the convection is not stochastic as such. Except,
but here you have stochastic forces everywhere.
Absolutely.
You can see it jumping around.
Yes.
You can see the fields.
Yeah, right, yes. Which of course does have a different correlation time than the actual forcing. Forcing is stellar correlated in time. So that's really high frequency in forcing, but not in the mean.
In the atmosphere, we know the fluctuation, the waves are generated in the troposphere below.
Yes.
On the sun, of course, it's different fluctuations. But you could, you could, in principle, try to run more like this and have fluctuations just from below to see how they propagate up.
Yes.
That would be more analogous.
Right. But first of all, now what would so as I said, this is a system which is actually periodic, and there wouldn't be any sense of up or down in the upper sense. So in that case, I think you can clearly rule out such an explanation. But you cannot rule out such an explanation, of course, in a more complicated other conditions.
One big difference, of course, here is that this is the convection zone which is neutral stratified. So you don't really have internal waves.
You certainly don't have internal waves in the convection zone because it's not exactly neutral, but it's, as we discussed, it is unstably stratified, but of course only weakly so because it has a large...
So what's the kind of waves you have? Albion waves?
You can have Albion waves, but they have a different frequency and they would also not be excited. I mean, they would be, they would only be excited to the extent that, the same as sound waves, that you are stochastically through the turbulence, in principle driving all kinds of other waves that are otherwise decaying. So Albion waves are, in the presence of scarcity, certainly decaying. They could not be self-excited. The mechanism that is pictured here is, of course, some mechanism where you have wave-like behavior which is self-excited, as was clearly shown by the mathematics. So, I mean, it would be interesting to go back to this problem and think about trying to approach both problems perhaps from mutually opposite sides. I have a little bit more here. If you can stop me if you want. One of this is this is a comparison of simulations where magnetic fields are being generated. It's also a non-trivial fact, of course, that you can have a conversion of kinetic into magnetic energy because you can write down a so-called anti-cowling theorem or anti-dynamo theorem by Cowling, which actually demonstrated that in 2 dimensions the magnetic field cannot be sustained. So anyway, nowadays we know that 3-dimensional turbulence can sustain magnetic field. Here is shown such an example. And here is shown the other energy spectrum in another example. So we have
so it's
yes, energy spectrum.
What was M?
E sub m meaning the magnetic energy spectrum. E sub k is the kinetic energy spectrum. And E sub t is the total energy spectrum, the sum of the two. So you see then something like a order of sub-range, together with something at large scales, depending on whether you have helicity, in this case, or no helicity.
So magnetic energy is larger?
In this case, yes, or in both cases, it's slightly larger in the inertial range. First of all, it's larger here even at the scale of the domain, where the kinetic energy is essentially zero, or very small. The magnetic energy really dominates. There's no kinetic energy at the same scale anymore.
So you have this inverse cascade only for the magnetic field?
Only for the magnetic field, yes. There's no inverse cascade for the velocity in this case. And that's how it looks like in real space then, at higher resolution. It's a function of the cube relation. Here's the same thing shown in a animation where you see the spectrum grows as a function of time and then saturates. The growth is exponential in time. So
what are the two curves?
This is the kinetic energy, just wobbling around because it's stochastically driven, in this case at large scales, and this magnetic energy spectrum. And again you see that it's a super equidistant with the kinetic energy.
So here you have the inverse cascade of the kinetic energy.
No, you wouldn't call it inverse cascade because it's driven at a large scale. So here you don't have any, here you just have direct cascades towards smaller scales. Here is shown an example where you drive at a scale, helically now, which is much smaller than the scale of the domain. And so in this case you see an inverse cascade, so let's look at that one. That's also a 5-curve cube simulation. It looks sort of slightly weird because this peak here but here you see this intermediate peak at its larger scale and then it propagates to the left. And that's really what we call an inverse cascade. Or inverse transfer, and I think the term cascade might be dubious because cascade would suggest that there's a continuous transfer along a spectrum, which is actually not the case. So you have a transfer directly from this scale to this scale. So it's not really inverse cascade, but an inverse transfer. Here again, such a simulation at high resolution, what such a thing looks like. You see the generation of large-scale phallons, but eventually they can point in various directions, in the x direction, y direction, or z direction, and one of the directions is randomly being chosen. And once it locks onto such a thing, it stays there.
But the forcing is specifically helical.
The forcing is helical, yeah. It's
So
isotropic.
that's in some sense cheating.
Yeah. It's a simple model of something, yes. I mean, it's cheating in comparison with nature. It's not cheating in comparison with the laws of nature. And therefore, it's also not cheating with respect to analytic models of this process that we can do. And the analytic models, of course, are running into approximations which are no longer controlled. And therefore, it's important to have a backup between simulations on the one hand and simulations on the one hand and analytic theory on the other hand. Right. You may not believe that the interpretation in terms of alpha effect actually has any basis, and there is a method which I can briefly explain that allows us to measure actually alpha explicitly in the simulation and actually the full tensorial nature of this, and even the fact that it is not even a simple coefficient between turbulent diffusivity, for example, and the mean shear matrix, for example, as you would normally make by assumption. I can show that, but in order to determine this for this equation, for the induction equation, which is here in curl, A is the vector potential, B is the curl of A, the basic method is, of course, to write down an equation for the averaged and to subtract this one from that one, in which case you get the equation for the fluctuations. And now the question is, can you find solutions to this equation for the fluctuations for a given mean magnetic field? And there's no need that we restrict ourselves to just one mean magnetic field, namely the one which could be a solution of this equation. We can do it for any mean magnetic field and solve this equation, therefore, as an inhomogeneous equation as far as magnetic field is concerned, because this term is independent of the magnetic fluctuations. So it's an inhomogeneous equation now. And this we can actually do. We can solve this equation for a set of different, as we call it, test fields. So we assume a certain field, which can be a sinusoidal field, something like this. It can even be time-dependent. So here's then shown how the method works. You make the general ansatz in terms of the tensorial relation between the electromotive forces U cross B term and the mean magnetic field and its derivative indicated by a comma. And then there's a tensor in between. And in order to calculate the first element of the tensor, alpha 1, 1, you can take a test field in the x direction alone, which has a cosine sinusoidal dependence. That means you have a cosine here, and the derivative gives you a negative sign over here. Now you have one equation, but you have two unknowns, this one and this one. Take now another test field, sine instead of cosine. You get another equation. So now you have two equations for the two unknowns. And you can solve that, and this is a solution. Looks like a rotation matrix, and this allows you then to calculate at every time and every position z this transport coefficient. So remember, this transport coefficient is now a function of time and one spatial coordinate, namely the spatial coordinate over which is the last one over which we didn't average. We averaged over x and y, and then everything else, the mean fields themselves depend on z still. So this is the method, and you can check that, you can compare it with analytic theories. And a simple analytic theory is one where you neglect this nonlinearity. And then you find, as a function of magnetic Reynolds number, that according to such an analytic calculation, which is fairly straightforward, for a simple flow field, and this is for a simple turbulent flow fields, or small-scale flow fields, it's not really turbulent, of course. You can check this method, you get a coefficient for alpha and turbulent diffusivity, which increases linearly with the magnetic Reynolds number. This is borne out by the simulations if you neglect this term. If you don't neglect this term, you find deviations from this, which can be also reproduced with a more advanced theory. So we know that these results are actually correct. But they do depend on the wave number of the test field. So here we come back to this. Of course, you have a wave number in here. So you can ask the question, what happens to a mean magnetic field that is on the scale of the domain? It's one answer. But what happens if you have a higher oscillation? And then you get different results. Each time you get a different result as plotted here. And in fact, for very high frequencies of the mean field, the turbulent transport coefficients become more and more inefficient, smaller, that is. Now, is this worrisome or not? And the answer is no, it's not worrisome. It's actually great. I come to that in one moment. Before that, let me show you what happens now with turbulence instead of the simple flow field. And we see that both the alpha effect and the turbulent diffusivity reach something which might look like an asymptotic regime. It's constant as a function of magnetic Reynolds number. So this is one of the indications why we might believe that even if we cannot reach 10 to the 11th, if it is a constant between these two numbers, why should it not be constant for much higher numbers? So it's a bit of a naive argument, of course, but it's at least an argument with which you need to shoot down, first of all. I mean, why should that, why do we expect it to eventually go down, for example, or even not to work at all? So, right, so I was talking about wave number dependence, but you should actually remember that the more general formulation is that you have no scale separation between the scale of the domain. Think of, for example, of turbulence which had large scale motions itself, which were now comparable to the scale of the motions of the mean magnetic field, or the scale of the magnetic field. In that case, you cannot simply write down such relation between a multiplication of the coefficient times the mean field. And in fact, you have to substitute it by a convolution over the remaining coordinates, which are here in space, but also in time. Now, a convolution, of course, corresponds to multiplication of wave number space. And here we have actually calculated the results. We have now the results for alpha for the various different wave numbers. So we can calculate this kernel by simply Fourier transforming backwards. This was the forward transformation, but of course it's a backward transformation. If you do the forward transform or the backward transformation to real space again, these are the measurements for turbulence, not the simple flow field I showed you earlier. It looks like a Lorentzian, which is 1 over 1 plus k squared. So it's proportional to k squared times the, let me write it like this, kf is the scale of the turbulent motions. And if you Fourier transform this, you get an exponential in space, modulus of the exponential. Yes, and we reproduce similar kernel types for other flow fields. These are shear flows in both cases. You have the same phenomenon also in time. Remember the talk by Lucarini yesterday? He was actually talking about susceptibility, and this is actually exactly the same thing. If you write it, this is now in temporal Fourier space and time, then this is what you could call it susceptibility, but not here, but in this case for the magnetic field, not for the climate response. So it's the same thing, and you have a real part and you have an imaginary part. It comes connects relations, of course, apply. So these can be all determined for different frequencies. So it simply tells us that if you are having mean fields that are no longer stationary, as they normally aren't, these coefficients will be depending on exactly the temporal behavior, how they decay. If you have a simple decay problem, for example, if you just have turbulent diffusion, you would think that the magnetic field should decay like e to the minus eta turbulent times k squared times t. But if it's decaying, it's of course not stationary. And if it's not stationary, then this itself might depend or should depend on the frequency omega. Or it's rather its imaginary part. In this case, of course, omega is minus the imaginary part times, minus the imaginary unit times the growth rate. That's the frequency in that case. And this becomes important, it's testable. Here is shown another example where you can actually see the discrepancy whether when you take it into account or when you don't take it into account. I think I shouldn't go too much into further such details here. And let me then try to wrap up. Yeah, one more thing. When I said you have we have also such an effect in time, then of course the kernel becomes more complicated. We now have indications that it actually more looks like this here, minus I omega plus tau to the minus 1 plus a coefficient, some kind of a turbulent coefficient times k squared. This is an approximate form of the response kernel both in space and in time. But the temporal bit can actually be derived also quite easily. If you look at the Cauchy scalar transport, calculate the average and the fluctuation equation for the average fluctuations of this, you can ask yourself what is the theory for the flux? And instead of just writing an expression for the flux, you can write down its time derivative straight away. Then you obtain this equation. So here you have an equation for the flux, and with its time derivative. If it's stationary, you would of course ignore the time derivative here. And then the flux, this flux would just be given by the negative gradient of the concentration, which is Fickian's diffusion law. But there is in principle an additional time derivative, which might not always be negligible. And so how does it look like in the actual equation then? The actual equation, of course, is one where the change of time of the mean concentration depends on the gradient of the flux, or the divergence of the flux. And I said the equation for the flux itself has this time derivative in it. So then if you put it all back in again, the diffusion equation looks like a damped wave equation nowadays. If you didn't take this time derivative into account, this would be absent, and you have just a regular diffusion equation. Now the problem with the diffusion equation is that you have infinitely fast signal propagation. And that doesn't even change if you apply similar concepts in general relativity, if you write it in covariant form. This problem of a diffusion kernel, which is phenomenologically derived, there's no theory, based on no more rigorous theory than just this one, it has infinitely fast propagation speed. So there's a problem with causality. But this problem with causality becomes alleviated immediately once you no longer drop this time derivative. And so in reality, instead of having a diffusion equation, you really have something which, in the limiting case of fast changes of the mean concentration, really becomes a wave equation. And this is a similar concept to the one where you have the Faraday displacement current, which you normally neglect. But once the changes of the magnetic field become comparable to the speed of light, of course you cannot neglect the Faraday displacement current, and that regularizes everything. And it's the same thing here, and it's the same thing with the inelastic approximation. If you have, of course, flow fields that become comparable to the speed of sound, then of course you cannot neglect the time derivative in your continuity equation. It's all the same thing. But here it's found at the level of neat field theory. This has all been tested and is by comparison. Right, I think that's my last page. These calculations we are doing with what we call the pencil code, which is a publicly available code. It's on the on Google code available. It's approximately 70 people, not 40. It was forget to change this page, who actually have access to modifying the code. Now you may wonder, how can you have so many people modifying one and the same code? And the way to doing this is by having an automatic validation of the code. Also, the code that people are seeing at any given moment is normally the one of the latest, of the last minute, of course, of the current state. And that, of course, I can show you also if I open my web browser here.
How do you recreate your results?
Yeah, no, we first of all, so by having automatic validation tests, you check, do you reproduce the same result as 5 years ago? Yes or no?
Exactly the same.
Exactly the same at the level of rounding errors.
Yeah.
Yes. Yes. So, of course, eventually there could be something which, so it's not, for example, point by point, but so let me actually find this here. Where do we find? Actually, by the way, it's even if you just Google for pencil code, then you find it.
So if you do a change in the pencil code that changes previous results,
Yes.
it will be noticed.
It will be noticed, yes. So, for example, we have here the test results on 10 different, a number of different machines. There's the hourly test, which involves, I think, 31 tests. And you see here the result of this, and you see there's one test out of 34, or 36? 36 failed. And that is something which has to do with sedimentation experiment. So this particular test fails, and we know actually there's one particular person who is in charge of this test, and that person should fix it. So if such a thing happened, somebody did a modification, of course, which we can trace back. The way to trace everything back is to run the order test. Everybody can run the order test. And then you can go back in time by going back to older versions, of course. So if you look at the page and you look at the changes in the source code.
So to do this, you go to this page, Google page,
Yes.
and then you download the code and run it.
Right. Yes.
Or rather, you get CVS or SVN, and then you say get pencil code.
I'm actually not signed in yet. That's why I don't see it here. Now I'm signed in, and I go to
What about parallelization?
It's fully parallelized, and it runs. Actually, you saw it from this page here. It runs on. Here's it scaling up to 4,000 processors. Here's on a number of different earlier machines, up to 1,000 processors. Yeah, so it's fully parallelized, and it works in also in circular coordinates, but it ignores the poles at the moment because it is a finite difference code. There is an issue, of course, we can't do that, and we also don't want to.
So it's the full MSD equations.
It's actually, yes, first of all, it's the full MHD equation, but there's more to that.
Doubly periodic? Triply periodic? Or what?
It's triply periodic, yes, it's three-dimensional. And it is, but it allows you, of course, to have all kinds of different things. First of all, there is the possibility of non-local radiation transfer in the code. There is self-gravity in the code. There is dust particles in the code. And there's chemical reactions in the code. So if you say it's an MHD code, then that's not a very good description because people are using this code to do, for example, hydrogen combustion. So there's really has nothing to do with magnetic fields, of course. So you have hydrogen combustion in that case, which involves about 20 different reactions. And of course, the reactions are temperature dependent and stuff. Here you see, as of right now, the latest changes. Here, Patrick Capella did a change 38 minutes ago. Then Anders from Lund did some changes 21 hours ago. Here's another guy from Lund who did changes 2 days ago. This is Simon who did changes 3 days ago. And this could be, yes. Yes, should I come? Yes, okay, I'm just speaking here and I'm wrapping up. I will come, yes. All right, can you take the meat, please? Yes, thank you. Yes, see you. Right. Yeah. So as you know, I'm in this Nordic board and I'm skipping that, of course, but now they tell me I should go for lunch. Anyway, so you got the idea of how this works, of course.
What is the star in the left?
These are my own changes. If you do the same thing, you should see it for your own changes. And as you also see here, of course, we have the revision number nearly 17,000 revisions. So you can then go back to a version like this here, for example, and check whether the code worked in that case. And if it worked, then you go check, does it work here? And then you say, yeah, it also works. And then here, it doesn't work. And then, of course, you know, the guy who did this was, in that case, was me, of course. Which can happen. And also, I mean, it's...
all these different versions are stored.
What?
All the old versions still exist.
Yeah. What is always stored is the differences. Yeah, you can go back to version number 1, which was written in 2001. Version 1 doesn't work, but at least version 150 already works. So you can have a number of different old plastic parts that all work. Right, I think with this, so I didn't really plan to doing this, but then when we have this cancellation by Kajan, who actually, she called me actually.
She called you?
Yes.
Where is she?
In Uppsala today. Because she is at the meeting in Uppsala now.
She has a meeting in Uppsala?
Yeah, but that's of course a problem, I suppose.
Okay.
But then I had to cut her short because I didn't want to, I could have used it to you, of course.
Was she yesterday in Uppsala?
I mean, who knows, maybe she was. Maybe she confused the dates. Anyway, right.
Could I ask one final question?
Yes.
I talked about such a, I mean, more or less you have a equipartition between magnetic energy and
Yes,
kinetic
yes.
energy.
In this case of post turbulence, yes.
Thermal energy and
Yes.
kinetic energy. I see. what is the case in the sun, in the convection zone? I asked Sasha Brown this question and he said that, oh, magnetic energy is much smaller
Yeah.
than thermal energy.
It is
Then
more.
Petri
Yeah.
Kepler said, no, you probably have equation. That's
Was that it?
Petri Kepler.
Petri. Yeah. I mean, it depends on how efficient the mechanisms are. Remember here in this
Well,
case.
but is something known from observations? Or is this a big unknown?
I mean, what we do know is that first of all, the magnetic field in sunspots has about 2,000 Gauss, which is actually in equidistant. Not only it is in equidistant with the turbulent motions, it's even in equidistant with the peak magnetic field, and it's also in equidistant with the kinetic energy, the thermal energy. So the pressure, the magnetic pressure and gas pressure are comparable. So it's very strong. The peak fields are very strong, but of course the magnetic field is very it's not space filling essentially. Now, as you go deeper down, it might well be that the magnetic field becomes more space filling, and the average field strength in the rest of the sun, that's at least what I'm thinking, is around 300 Gauss, and the equipartition field strength is more in the order of maybe 2,000 Gauss, or 3,000 Gauss. So it's a tenth. Magnetic field strength wise, it's a tenth below equipartition.
And the gas, or is
yeah, one could say this is the gas. This comes from mixing length theories, which are fairly accurate for the sun, as far as the RMS velocity is concerned. Yes, I would say it is a guess or even an opinion. Some people are saying actually it should be zero, and all the magnetic field is essentially at the bottom of the convection zone in the tachocline. But that's something which is also an opinion. And if you have any simulations, you find that the magnetic field is actually distributed throughout the sun. So if you look at Sasha Boone's simulations, a number of other simulations, also our simulations, the magnetic field is always distributed throughout the convection zone. There's no reason why the place where the magnetic field has a chance to be generated, why it shouldn't be at that location. Why should it be only at the boundary between where it can be generated and not be generated? That's a very tiny layer, and it's a strange guess. In hindsight, perhaps. I mean, the reason, there's a good reason why people think the magnetic field should be in the tachocline. The reason is the tachocline, remember, is a layer where you have, it's the bottom of the convection zone, and in all these places, if you put a magnetic flux tube here, it would rise because of magnetic buoyancy to the surface, and it would do so in a time scale of no shorter than 50 days. That's short compared to the 11-year cycle. So therefore, based on that idea alone, you would be thinking the magnetic field would be lost, and you cannot actually keep it there. However, this is based on magnetic buoyancy, and this is not a correct interpretation, as was already clear since the last 20 years. What you actually find in simulations instead is a much more important effect from downward pumping. Magnetic field is pulled downwards by the turbulent motions. And the turbulent motions are non-uniform. The turbulent intensity has a gradient with height. Put it like this. What I'm showing is u squared as a function of radius. As the largest velocity, of course, you have near the surface, and the smaller velocity has the bottom of the convection zone. And the effective pumping velocity comes mean magnetic fields down this gradient of turbulent velocity, and that's according to theory. But that's also what you see in
rephrase
simulation.
this more simply. So this is beta parameter. Okay. It's basically pressure divided by magnetic pressure.
Yes. Yes.
So I asked Sasha Brown about this.
Yes.
40 feet in the direction zone. He said it's very large.
Yes.
Petri Kepler said it's order unity.
No, that must be a misunderstanding. So at the surface, for the strongest magnetic field, it is a Ward unity. As you go deeper down, it becomes smaller and smaller. Because here you're talking about the gas pressure.
Yeah.
So it's an extreme location.
That's what I asked him.
Then you misunderstood, perhaps. I mean, as you go down into the bottom, here, as you go further down, the gas pressure, of course, increases dramatically, but the turbulent velocities decrease. And they have to decrease because they have to carry the same convective flux. So the flux is approximately this. The RMS velocity to the third power times the density. So as the density goes up, pressure goes up, but the velocity must go down. And if the velocity goes down, the magnetic field goes down. And that makes the plasma beta even more extreme. Because now this one goes heavily up, velocity goes heavily down, and the magnetic field goes down, because magnetic field and the velocity have something to do with each other, not with the gas pressure. It's only once the magnetic field does become for other reasons, because if the pressure towards the surface drops significantly, it actually, of course, it's not the end of it. You go beyond the sun, right? You go to this position. The gas pressure just continues falling down, and the magnetic fields don't fall down so much. And then you have very low plasma betas in the outer parts. And that's why you actually have also a corona. So you imagine now you have these magnetic field lines that are in a medium with very little momentum. These magnetic field lines moving back and forth, they produce a lot of shaking of these motions, and they lead to and even produce heating by magnetic field lines.
You have trouble equilibrium with kinetic energy, but not the
Yes, and this also only within a factor of unity, of course. This, of course, is defined as the square root of rho times the RMS velocity squared times the permeability. It's proportional to the RMS velocity. Yeah, so I think I did maybe at least explain a little bit what I'm doing then, and I think there's a little of connection. I think, for example, the stuff which Lucarini talked about was very interesting to me, and I talked to him about these things. Of course, our coefficients alpha, they are also fluctuating in space and time, and that's one other very important issue that we're looking into. This can have non-trivial effects. Backscatter is one of them. There's a lot of interesting things that we learn about, and of course, there's the whole issue of perhaps predicting space weather. By space weather, I mean, on the one hand, we have the solar cycle on the long term, but we also have effects on much shorter time scales.
I think we might want to speak about space weather and space climate, and solar cycle as a kind of a space climate or technical. So separate the solar cycle prediction and don't call that space weather, but something else.
Oh, what should we? Oh, okay. So people call it subsurface weather. Is solar subsurface weather or something like this?
That is for the short term.
Yes.
That's why. But 11 years, we might want to call something else than space weather.
Oh no, I don't actually call it space weather. Nobody actually calls it space weather. But of course, it's maybe more the climate. It's maybe space climate.
Space climate.
Yes. Anyway, so thanks to everybody for coming to this program, to the remaining people here, and we had an exciting time. I hope many of you learned something and got something out of it, and more time to be spent, of course, on doing more. Everybody can propose such a program. Nordic program is not strictly not limited to anybody from the Nordic countries even. So if anybody from the US or from London or something wants to propose a program, please do that. And typically the application deadlines are the 15th of December each year.
For the next year.
Yes, I mean for the foreseeable future. We are facing, of course, the budget issues, which means that, and in fact, program activity is one item that might actually be the most unstable one. If you don't have enough money, we might keep postdocs, but we might actually skip or reduce the funding of the programs. But
how many programs are there typically every year?
How many? We have typically between 8 and 9 programs.
Per year.
Yes. And there's an independent committee which evaluates them. Should turn off the camera here. Okay.